We are Team 5, and this is our final presentation on the analysis and redesign of a stapler.
Our selected product is a standard manual desk stapler. It fastens paper by using a spring-loaded lever to drive a metal staple through the sheets. Typically includes an injection molded plastic housing, stamped sheet metal parts, springs, pins, and rubber feet. We chose it because it has between 10 and 20 components. It is mass produced at about 200 million units per year, and it uses course-related processes like injection molding, sheet metal fabrication, machining, and assembly. The primary customer group is everyday office and school users, such as students, teachers, and businesses who need low cost, reliable, easy to use stapler. The secondary customer group is a high volume professional users, such as legal offices or departments that staple frequently, where durability, comfort, and staple capacity matter more. Here's an exploded view of our item showing all 14 parts. The core function of the stapler is to fasten paper, whereas sub-functions include place staple, load staple, and assuring the product is convenient, dependable, and enhancing the product. As shown in the function component mapping matrix, the main takeaway is that it is pretty well balanced. All components have several functions, at least more than two, and no single function needs over 40% of the total components. This is because a stapler is already very efficient and optimized. Nonetheless, there are still areas for redesign and potential improvement.
After comparing the functions of the FAST diagrams with our primary and secondary customer groups, four functions were different. That being prevent slip, improve appearance, improve grip, and reduce effort. When looking at the component commonality, the only modules that deal with these four functions are the top plastic housing and the rubber base pad.
For the design for manual assembly, one module and one platform part were selected. On the left, we have the return spring, which is a platform part. For this part, we reduced the thickness to meet DFA 10, increased the radius of curvature to meet DFA 7, and altered the geometry to meet DFA 6. The geometry was also altered to meet DFA 6 for the plastic housing, which is our modular part. On top of this, we increased width to meet DFA 4 and changed its color to meet DFA 9. Here you can see the pre and post DFA charts and how assembly time and efficiency were improved from these redesigns. The parts we chose for redesign were selected using the quad and function mapping charts. The quad chart proved most useful, especially in showing that the upper cover was expensive and not very important, which made it key for redesign. For the platform part, it showed us that this part isn't expensive to manufacture, but is to assemble, making it another prime candidate for DFA. Overall function should remain the same, if not better, for these parts. And while increasing manufacturing costs may be possible, it is definitely outweighed by improved assembly efficiency, seen as these are minor changes.
The design for automated assembly analysis is completed based on the platform subassembly that is made of the upper metal frame, the hinge linkage, the staple rail, and the hinge pin. They are justified as they both have high importance and high manufacturing cost in the quad chart, other than the hinge pin, which is high importance but low cost, but it's still included as is part of the assembly. As seen by the chart, the total automated assembly has a total handling and insertion cost of about 17.2 cents. After redesigning the part, the cost reduced to about 10.2 cents, a 7-cent decrease, which is pretty good given how efficient for assembly staplers already are. This slide shows the before and after of the automated assembly analysis. The main takeaway is you can see that the part count was reduced by combining the upper metal frame and the hinge linkage. This combination also allowed for the minimizing of turning over for assembly, and thus implements both DFA1 and DFA12. Additionally, adding fillets to the insertion hole on the upper metal frame allows for the hinge pin to be inserted more easily and reduces insertion cost by a bit. But when looking at the large quantity of production, it makes a difference.
For the process selection for plastic, we use baselines given from the original plastic covering that's in blue. Due to having tighter requirements like mass as it's bigger and section thickness is a little smaller in areas. We also use basic tolerance for the plastic at 0.5 millimeters. With all these requirements and more, we found machining, injection molding, and blow molding were compatible with polypropylene, and injection molding was our selected process out of the three.
After analyzing the plastic housing in DfM Pro, the recommended improvements were for uniform wall thickness, which is shown above, the minimum draft angle, which was shown below, and recommended rib parameters. The before attributes can be seen in the top right, with the notable attributes being the volume at over 11 cubic centimeters and the wall thickness at 2 millimeters. After analyzing each the part for the costs, we determined that the total cost per part would be 0.1161 prior to adjusting. In order to improve the design for manufacturing aspect for the plastic housing, we applied design for injection molding 1, 2, 4, and 5, which included reducing wall thickness, improving wall thickness uniformity, reducing sharp corners, and adjusting the rib thickness to a better ratio of 60% of the wall thickness. The after attributes shown above include a decreased volume of 8.46 cubic centimeters and a decreased wall thickness of 1.5 millimeters. This leads to a total cost per part of $0.0901 or a reduction of $0.026 or around 22%.
For the process selection of metal, we use less restrictive conditions like mass and surface roughness to allow for the redesign of the top metal frame. With these restrictions, we found machining and sheet forming would work, but sheet forming was picked out of the two options. Finally, steel was selected to be the material used for the part.
This is our sheet metal bracket. DfM Pro flagged 4 rules, 1 being critical from bends running in opposite directions, 2 high from cutouts and slots sitting too close to the edges and bends, and a low bend radius. In the redesign, we applied a few sheet metal guidelines. Next slide. DFSM 7 pulled the holes and cutouts inward, which cleared the entire cut to edge problem. DFSM 9 raised the near zero bend radii, and DFSM 1 cleaned up the geometry, so the part now fully analyzes. Together, that took us from 4 flagged rules down to 3, and we kept the jog as a functional exception under DFSM 2.
Design for product service system. Our proposed product service system would focus on refill, replacement, and take-back program for high-volume users. Customers could order staple refills and replacement wear parts such as rubber base pads or springs, instead of replacing the entire stapler when small components wear out. This improves the customer experience by reducing downtime, lowering long-term replacement costs, and making maintenance easier for offices that staple frequently. Additionally, offering different top plastic housing colors can be included as a low-cost customization option, since the housing design remains the same across variants. To reduce environmental impact, the housing can be made from recycled plastic, and worn staplers can be returned through a take-back program so the metal and plastic components can be separated, recycled, or reused. In conclusion, manual assembly improved efficiency from 0.416 to 0.432. Automated assembly had about 7 cents in cost reduction. Top plastic housing cost reduced by 0.026 cents, or about 22% of original assembly costs. Space the holes and cutouts farther from the top metal housing's edges and bends. Our critiques are manufacturing costs for plastic housing could increase due to more material. There is slight addition to the stamping complexity, and common desk stapler is already very optimized and efficient, making it challenging to redesign. If we had to start over, we would target the stapler mechanism earlier and prioritize part consolidation in the high function metal subassembly. We would also evaluate materials substitutions only after confirming durability, wear, and staple forming requirements. Thank you